picking up where we left off last time, we had gotten the skeletal equation for this chemical equation. We learned about balancing chemical equations, and this is what we will learn later is a double replacement reaction. So it doesn't balance quite as nicely as the way that some of the other ones do. I'm looking at you, combustion reaction. And so we have to use, it's ideal, in my opinion, to use a slightly modified version for balancing these. So we're going to look for something that's different on the left side, the reactant side, versus the product side. We've got two things that are that. And since I've written the twos in red, they point out pretty nicely. So iodine, or iodide in this case, and potassium. So if we are balancing for iodine, how many iodines do we have on the right side? We've got 2. How many do we have on the left side? We've got 1. To get those to balance out, we need a 2 in front of our Ki, potassium iodide. When we change that, our iodine is now balanced. We've got the same number of I's on the left and the right, 2 I's. That's the correct number of I's, some would say. And we've got now 2 potassium. So our potassiums has changed. We're going to balance potassium next. So let's look at potassium. Okay. We've got 2 on the left side and conveniently 2 on the right side. Usually this signals we're done, but we still want to check because it won't always work that way. I think it's possible that it won't always work that way, so we want to check everything else. So lead, Pb, 1 on the left, 1 on the right. There they are. And we've also got sulfate. Sulfate is a polyatomic group, and our sulfate group is sticking together, so SO4s. We also have 1 on the left, and we've got 1 on the right. So everything is nice and balanced, and all we had to do is add 1 single 2. Nice. That's about as easy as it gets, other than it just already being balanced, which does happen sometimes. It's just rare. Balance this chemical equation. I'll give us some time to work on this, get our brains engaged in case we're still a little sleepy from waking up. So we've got HCl reacting with O2 to form H2O and Cl2. Figure out what our coefficients are in front of each of those. This is our more normal type of balancing equations. All right, hopefully at least enough time to make some progress, or to make no progress and realize, oof, got to study. Either way, an okay outcome. So we've got a couple of compounds. We've got HCl, we've got H2O. Oxygen and chlorine are just the atom by themselves, or the molecule, the element by themselves, and so we can leave those for last. The one thing that we do have that's in a compound on both sides is hydrogen. It's in HCl, it's in H2O. So we're going to balance hydrogen first. Currently we've got 1 on the left side, we've got 2 on the right side. To get those balanced, we want to add a coefficient of 2 in front of our hydrogen chloride, or hydrochloric acid if it was aqueous. That'll get our hydrogens nice and neatly balanced up. And then after that, we can balance whatever we want. It doesn't matter. So let's look at our chlorine next. So Cl, we've got 2 on the left side because of our coefficient of 2 in front of HCl. We've also got 2 on the right side because of the subscript of 2 behind Cl2. Then the last thing to balance is that we've got oxygen. So we've got 1 oxygen on the right side, and we have 2 oxygens on the left side. There are 2 ways that we can get our oxygen to balance. One of them is faster than the other. The way that you might think of balancing these is, oh, well, just add a 2 in front of our H2O. That'll get our oxygens up to 2, and that's true, but it'll also change our hydrogens and make it 4 hydrogens. And then we have to go over and balance our hydrogens on the left side, and that's going to screw up our chlorines. Then we'd have to balance the chlorines on the right side. You can do it that way. Sometimes it turns the problem into an absolute nightmare, and so I don't recommend doing it that way. The better way, the way that I would recommend doing it, is adding a coefficient in front of O2. What can we add in front of O2 to make it so there's only one oxygen? 1/2. And now we've got one oxygen on each side. But we have a problem, right? We can't have half of an oxygen molecule because oxygen molecules come in whole units, just like we can't have half of a student. Students also come in whole units. And so we have to get rid of this 1/2. And the way that we get rid of that 1/2, who remembers? We're going to multiply. We're going to multiply everything by 2. Since it's all balanced, when we double the amount of stuff we have on the left side and double the amount of stuff on the right side, it's all going to get doubled. And so it'll still be balanced. So instead of 2 HCl, we're going to have 4 HCl. Instead of 1/2 O2, we're going to have a singular O2. Instead of 1 H2O, we're going to have 2 H2O. And instead of 1 Cl2, we're going to have 2 Cl2. And then to be rigorous, to be diligent, we would go back through and check the number of each that we have. I definitely recommend double checking your work on exams. So that concludes, I think, basically all we're going to talk about balancing reactions. I will walk through some of the steps again because we're going to do more balancing reactions. But these are skills that we'll hopefully be practicing on our own time, either by doing homework questions, doing practice quizzes on Canvas, or some other way. And now we're going to learn about some types of reactions. There are lots and lots of ways to categorize chemical reactions. We're going to learn 4 basic categories. So we're going to learn about combination and decomposition. Those are sort of opposites. We're going to learn about single replacement and double replacement. I've talked about double replacement a little bit. And we're just classifying these based on how many things we have on the left side, how many things we have on the right side, and what do they do. We're also going to learn a few specific types of reactions, like combustion. So our first one up, we've got combination reactions. When you're combining things, you're putting them together, and that's what we're doing in a combination reaction. We're taking 2 substances or more, A and B, just putting whatever we want there. You add those 2 things together, and you get one thing out on the right side. It's sort of a 1 + 1 = 2 situation. We would also call these synthesis reactions. And the general form is A plus B turns into AB. Sodium metal reacting with chlorine gas is an example of this. It makes table salt. It's a violent reaction. Produces sparks. Lots of energy is released. So these are combination or synthesis reactions. And you should be able to classify, if I give you an example of a chemical reaction on the exam, which I will do, you should be able to identify which of these 4 classes of reaction does it fall into. We also have decomposition reactions. And decomposition reactions are the opposite of combination reactions. Because instead of 2 things going into one, it's one thing turning into 2. It's decomposing, it's breaking down into its individual parts. These decomposition reactions usually involve an input of energy, either as heat, light, or electricity. Carbonic acid, which is in soda, decomposes to CO2 gas and H2O. That's how the CO2 gas, some of the CO2 gas gets stored in your carbonated beverage. It does eventually usually leave by itself. So this is our decomposition reaction. One thing turning into 2 or more things. Could also be 3 or more products. Usually it's 2, but sometimes it's 3. There's probably an example with 4 or more. And then our first type of specific reaction is combustion reactions. We've already talked about combustion reactions a little bit. Combustion is just burning stuff, right? Making flames. We love combustion reactions. Sitting around and watching things burn. Or at least lots of us do, I hope. So a combustion reaction occurs when we have fire. Fire, just like us, needs oxygen to breathe. And so it reacts with oxygen, it produces heat, and it also produces light. A lot of the time we are doing combustion reactions for heat rather than for light, since we have electrical lights now. So heat, like to cook stuff on our stove at home if we've got a gas stove, on our propane grill outside in the backyard. If we like grilling in the backyard, maybe we're burning charcoal, maybe we're burning actual coal. And we would also sometimes do them for light, like campfires or burning candles. Combustion reactions of substances with carbon and hydrogen, or carbon, hydrogen, and oxygen, always produce carbon dioxide, CO2, and water. So carbon, hydrogen, oxygen compounds for combustion react with O2, oxygen gas, to form CO2 and H2O. I think I talked about last class how if you see water pouring out of somebody's exhaust pipe on their vehicle, this is where the water comes from. It's from the combustion reaction. It's just condensing in their tailpipe because it's colder outside than it is in the explosions happening inside of their internal combustion engine. So that's where the H2O comes from. The CO2 that's produced is why you should open your windows, assuming that it's reasonably nice outside or just not terribly, terribly stinking hot outside. You should open your windows to get some fresh air in to dilute the carbon dioxide that's produced when you're cooking food. The levels can get up to where they're like starting to affect your ability to think. It's probably not going to get high enough that you're going to, perish. Probably. Rare instances where that might happen. As long as you're in a reasonably well-ventilated space, you shouldn't have to worry too much about the CO2. Or if you've got a hood that vents to the outside on your stove, you can turn that on and that'll pipe some of the CO2 out as well. So the way that we identify combustion reactions, we're reacting with O2, we're forming CO2, carbon dioxide, and H2O. This is a definition, an identity that I expect you to know. The oxygen part here is optional. The example that we've got here, we've got propane, the thing that you would use for outdoor grilling typically, reacting with oxygen to form CO2 and H2O. If we added an oxygen onto this, like if we were burning a sugar or an alcohol, that would also have oxygen on it. That's also going to turn into CO2 and H2O. Here's an example of what we might see on an exam. Octane is a component of gasoline. Write the skeletal equation for the combustion of octane, then balance the equation. This is probably harder than what would show up on the exam. This is a sort of thing. I might ask you to balance this and then give me the coefficients. And all I'm telling you here is octane, and I'm telling you what octane is. So octane, C8H18. What two elements do we have in octane? Carbon, hydrogen. We don't have any oxygen in this case. So this falls under the definition of combustion that we should know. We don't have to have it memorized immediately, but later on we'll have it memorized. What's the other thing that we're going to use as a reactant when we're doing combustion, like for octane? Oxygen. Fires, candles, burning things also need oxygen to breathe. If you're burning a candle and you put the lid on, assuming that it's the type that has a lid, what happens to the flame? It goes out. It uses up all the oxygen that's in the container and it can no longer burn. This is also why grills often have vents on the bottom, or stoves or outdoor things, they usually have some way of getting extra air in. If you're having trouble starting a fire, it's possible that you've just lumped all of your material together and you're not getting enough airflow in, and so your fire can't burn, it's choking itself. What are our products? Carbon dioxide, CO2, and H2O. So this would be our skeletal equation for the combustion of octane. And then to balance it, we need to follow our steps for balancing. So we're looking at what first? Carbon. Why carbon?
It's part of a compound.
Yeah, it's partly it's the first one, but it's also in a compound on both sides. So carbon's in one thing on both sides. That's got other chemicals in it or other elements in it. Hydrogen is in the same boat. It's in the octane. It's also in the water. You could balance hydrogen first if you wanted to. It doesn't really matter. It shouldn't matter. So we've got 8 on the left, and we've got 1 on the right in our CO2. We're going to have to bump those numbers up. So we add an 8 in front of our CO2. Now we've got 8 and 8. We're nice and balanced with respect to carbon. Taking time so people can write. Next, we're going to be balancing our hydrogen. We've got a lot on the left relative to what we've been doing so far. We've got 18. 18 on the left. On the right, we've only got 2. So to get that 2 up to 18, 2 times what equals 18? 9. Now we've got 18 hydrogens on the right side because we've got 9, our coefficient in front, times the 2 in each water. So now our hydrogens are balanced. We didn't change our number of carbons, so that's still balanced. The last thing to balance out is our oxygen. And for our oxygen, we've got oxygen in 2 compounds on the right side, so we're going to have to add those up. We're going to do 8 times the subscript of 2. So 8 times 2, and we're going to add to that the 9 from our H2O, because we've just got 1 oxygen. So 9 times 1 is 9. So we've got 8 times 2 is 16, plus 9, make it 25. And on the left side, we've got 2. Is 25 an even number? It's not an even number. 2 is an even number. We can only multiply it up to get even numbers. If we're multiplying by whole numbers, that means we're going to have to use a fraction. So what times 2 equals 25? 2 times what equals 25? 12.5 is the correct answer. Can we have 12.5 oxygen molecules? We cannot have 12.5 oxygen molecules. You could also write this as 25 over 2 if you wanted to. They're the same thing, different ways of writing it. When we do that, now we've got 25 oxygens on the left. It's completely balanced, but we've got that fraction. What do we do to get rid of the fraction? We multiply. What do we multiply by? 2. Multiply by 2. So we're going to go through and multiply everything by 2. So 2, C8, H18, plus 25, O2 goes to 8 times 2 is 16, CO2 plus 9 times 2 is 18, H2O. And then because we multiplied everything by 2, it would be a good idea for us to go back and check and make sure, did we actually multiply everything by 2? Because sometimes we miss one. So we did 2 times 1, that's 2. 2 times 12.5, that's 25. 2 times 8, that is 16. 2 times 9, that's 18. Okay, so we're good. And then to be extra diligent, we would go back and double check the amounts of everything, but I'm going to skip that because I'm assuming that we can do that. And I'm a little lazy. So that's combustion reactions. We talked about 2 types of reactions before getting to combustion reactions. Does anyone remember the names of those 2 types of reactions? Composition or combination synthesis, not composition, combination synthesis, putting things together, and tearing things apart, decomposition. We also have single replacement reactions. Replacement, swapping something out for another thing, replacing something. We're doing only one of them, so it's one thing being replaced. And the general form for these is A plus BC goes to AC plus B. So A and B have swapped places. So instead of B being with C, A is now with C. So we've swapped out one of our chemicals. You could also have it so that A swaps out C instead. An example of this is when metals react with acids, they produce hydrogen gas and a salt. Typically a salt. In this case, that salt is zinc chloride. So zinc and hydrogen have swapped places. So instead of hydrogen being with chloride or chlorine, it's now the zinc that's with the chloride. Why did zinc swap for the hydrogen instead of swapping for the chloride?
Because zinc has...
What kind of charges do these have when they're ions? Zinc has what charge when it's an ion? Is it positive or negative? It's going to be positive. What about hydrogen when it's an ion? Also positive. And what kind of charge does chlorine have when it's an ion? Negative. So HCl together, we've got a positive and a negative. Zinc forms a positive charge, and so it's going to swap out for the thing that has a positive charge. If it swapped out for the chlorine, then we'd have 2 things with positive charges together, and that doesn't work in chemistry. There's also double replacement reactions. Double replacement reactions, rather than just swapping one thing, we're swapping 2 things. These are also sometimes called displacement reactions. So single displacement or double displacement reactions. A double replacement reaction occurs when the positive and negative ions swap, we're switching dance partners, to form new compounds. And so that has this general form. In this case, our B and D have swapped. And this should probably be written CB. Not CD. It's maybe less confusing if I had written it CB instead of writing it in alphabetical order. We will talk about how we predict products for single and double displacement reactions, double replacement reactions. One type of replacement reaction is precipitation reactions. 2 aqueous solutions can mix to form a precipitate. And our definition for a precipitate is that it's an insoluble ionic compound. So I'm sort of overlapping 2 different definitions here. Our definition for a precipitation reaction, 2 aqueous solutions. Aqueous means they're dissolved. because they'll have the AQ after it. Two aqueous dissolved solutions mix and they form a solid. That's our definition for a precipitation reaction. And then the precipitate is just the solid that forms. So what comes out of a precipitation reaction, the reason that we do precipitation reactions. Does anyone have questions about our synthesis or combination reactions, decomposition reactions, single replacement reactions, or double replacement reactions? All right. We can also predict reactions. We talked about this a little bit in single replacement reactions, but let's look at it a little bit more closely. So single replacement reactions involve one element substituting with another, and this generates new products. Arguably, these are more difficult than double replacement reactions, arguably. So when the reactants are an ionic compound in an element, the element replaces the element that it is most like, and we're thinking about positive or negative charge. Remember that cations, cats have pos, so cations are positively charged. And anions look like onions, and onions make you cry, and crying is not always bad, but we generally want to avoid crying, so we can think of anions as being negative. Or however you like to remember. So looking at this example, ferrous chloride reacting with calcium. What kind of thing is calcium when it's an ion? What charge does it form? Yeah, it forms a 2+. And our iron is going to form what charge? It's also going to be a 2+ charge. Our chlorine is going to form what charge? Yeah, it's going to be Cl-. So we are figuring out, okay, calcium's a 2+ charge. It's a positive charge. It's going to swap out the positively charged component in our compound. So calcium swaps out iron because they are both positively charged. They are both cations. So we're going to swap calcium in for our iron 2. So calcium 2+ is getting paired with Cl-. We have to do our flag and drag. CaCl2. And of course, flag and drag is not what we're doing. It's swap and drop or crisscross. I'm just being silly. And then the other thing that we would have is iron, just as a metal by itself. We could also go ahead and double check that this is balanced. We've got one calcium on the left, one calcium on the right. We've got two chlorines on the left. We've got two chlorines on the right. We've got one iron on the left. We've got one iron on the right. So it's balanced. We don't need any coefficients. You'll love to see it. And then what about MgBr2 plus F2? What kind of ion is F going to form? Negative. It'll be F- when it's an ion by itself, monoatomic ion. What about magnesium? Magnesium is going to be a 2 positive charge, 2+. And what about bromine? Bromine is going to be bromide, the negative ion. So F is most like which one of these two? It's more like bromine because they both form negative charges. So F swaps out Br because they're both anions. And so on the product side, we are going to see MgBr2 doing that same crisscross thing, and we're going to have Br2. And I wrote the wrong thing. MgF2 and Br2. Miley was right. Everyone makes mistakes. So that's how we predict for single replacement reactions. For double replacement reactions, there's more work, but I think it's simpler. So let's look at double replacement reactions. Double replacement reactions, we are swapping the anions between two ionic compounds. The anions are the negatively charged parts, the latter half of the compound. Strictly speaking, you don't have to swap the back half. You could swap the front half instead, as long as you're swapping them. So to predict the products, we're going to separate the ionic compounds into cation and anion. So we're going to take, in this case, the barium and the chlorine. We're going to separate those out. We're going to take the lithium and the sulfate, and we're going to separate those out. Then we're going to swap the barium and the sulfate, and we'll recombine and make sure that the charges are balanced. This is why I said there's more work, but arguably it's simpler because we don't have to identify which thing are we swapping out. We're just mixing them up. We're swapping the anion. We're swapping the negatively charged part. What does this look like? It looks like this. Write a balanced reaction for the reaction that occurs when barium nitrate and potassium hydroxide are mixed. What's barium nitrate? What's barium? Ba. And what's the charge? 2 plus. Barium is also what you do with dead chemists. And what's nitrate? Yeah, nitrate is NO3 minus. And that's one that shows up on your green sheet. So you would get that on an exam. You would have to recognize that we've got the ATE ending. So don't go looking at nitrogen because that would be nitride. The ATE ending means we've got an oxyanion. So we're mixing these two things. These are combined. So we do our crisscross. We've got Ba, open parentheses, NO3, close parentheses, 2. And we're reacting this with potassium hydroxide. Potassium is K plus. Hydroxide, we've got the start for hydrogen, hydra. We've got ox. So that means we've got hydrogen and oxygen. The "ide" ending means it's negatively charged. So this is OH minus. It's a 1 plus and a 1 minus together. Those balance each other out, so it's just KOH. So those are our reactants. To be fully diligent, we'd go ahead and add the AQ. We're assuming they're dissolved. So that's our reactant side. Our product side is going to be a mix-up. We're going to remix it. So we're going to swap the nitrogen and the hydroxide. We've already got them split up into their halves, into their ions up top, so I'm going to reuse those. So we're going to swap our nitrate and our hydroxide. So rewriting on the product side, we're going to rewrite the barium ion, Ba2 plus. It's now paired with hydroxide. So put the OH minus next to it. And we've also got our potassium, K plus. We rewrite that, and that's now paired with the NO3 minus. So NO3, 3 minus. And we can combine these ions together to form our compounds. So Ba2 plus with a 1 minus, we're going to need 2 of those, which is what we would get if we swap and drop. So Ba, open parentheses, OH, close parentheses 2, and we also have KNO3. We've got a 1 plus with a 1 minus. Those balance each other out because they're equal and opposite, so we just put them together. Do we have a balanced equation? Balanced reaction? We don't. So we have done the first and second steps, because I think the second step was make the skeletal equation, something like that. We've still got work to do is what I'm saying. What is one thing that's not balanced? The hydroxide is not balanced. We've got 1 on the left, 2 on the right, so we can start balancing hydroxide. 2 on the right, 1 on the left. To get those to balance out, we want a 2 in front of our KOH. So cross out that 1, make it a 2. I'm going to change the colors on these. Let's do blue. 2 on the right, 1 on the left. So we put a 2 in front of our KOH. Now we've got 2. What are we balancing next? We are balancing K next because we just changed K. So K, we've got 2 on the left. We've got 1 on the right. That's not balanced. We need a 2 in front of our KNO3 on the right side. That will get us up to 2 Ks on the right side. So that's balanced. What are we balancing next?
Nitrate.
We're balancing nitrate because we just changed the amount of nitrate that we have. So looking at our NO3, we've got 2 on the right side because of our new coefficient of 2. And look at that, we've got 2 on the left side because of the subscript of 2 outside of our NO3. Usually, for double replacement reactions, this means we're done, but we do want to make sure that we are actually done, so let's check barium. Ba, we've got 1 on the left, and we've got 1 on the right, so we are nice and balanced. Questions? Does it feel like it's a lot of steps? I'm seeing people nodding their head. I'm seeing some people looking less than confident. We are going to have to practice doing double replacement reactions before we feel confident in them, before we feel like we're ready to go, Mr. K. Give us exam 3. So there's homework questions once we finish the chapter that you'll have that you can practice these. You can go see Logan. He would love to make some double replacement reactions for you to practice balancing. You could also see Jonathan or Liz in the STEM room from noon to 5, Tuesday, Wednesday, Thursday today. I also have office hours today, 1 to 3, to make up for missing office hours yesterday. So those are some places you can go to get help. And this is one for us to try. Predict what will happen if rubidium hydroxide and cobalt-2 chloride are mixed. What I'm looking for is a balanced chemical equation. So we'll spend some time on this. After a couple minutes maybe, I'll just give us the starting chemicals. After a couple more minutes maybe, I'll give us the whole skeletal equation, and then we'll go through and balance it together. All right, if we were having trouble launching the problem, for nomenclature reasons perhaps, rubidium hydroxide, rubidium is Rb, hydroxide is OH, rubidium's a 1 plus, hydroxide's a 1 minus, so it'd be RbOH. And then cobalt 2, this 2 means that it's a 2 plus, and so it's going to be CoCl2. Chloride's a 1 negative charge, so when we swap and drop, we'll end up with CoCl2, and that's our reactant side. Then we just have to swap our anions and recombine them so that they're neutral to get our products, and then balance. Okay, so we were looking for what do we get out of this? And to figure out what we're getting out of a double replacement reaction, we need to swap our anions. So we're swapping the latter half. And the way that we would do this, if we were provided the starting chemical formulas, this is how I would do it. I would separate these into their component ions. So Rb is going to be Rb with a 1 plus charge. OH is a polyatomic group, it's hydroxide, so that's going to be OH minus. From our CoCl2, we've got cobalt. The cobalt is a 2 positive charge. We could figure that out if we weren't told it from the number of chlorides that we have. That maybe takes us back to thinking about our nomenclature when we were doing this for ionic compounds. Chlorine is going to be a Cl minus. So those are the individual ions that we'll have. And then we have to swap. And the swap happens with the anions. So the negatively charged ions, we're switching their places, and we're going to rewrite those with their new partners on the right side. So we've got Rb plus paired up with our Cl minus. And our other thing, we've got the cobalt 2 plus paired up with our OH minus. One of the things that I was seeing a couple of people were mixing up was that the O on CO2 plus, we were writing this as a capital O, and so it looked like we were writing carbon and then oxygen, and then we were maybe putting a 2 as a subscript, writing it as CO2, and that tripped a couple people up. This is cobalt, it's capital C, lowercase o. Those are different and important. And then the 2 positive charge. And then we're going to recombine these to get our products. I recommend writing out the individual ions so that we make sure that we're putting in the correct subscripts when we're recombining them. Until you get really confident, really practiced at this, this is the way I recommend doing it. So for rubidium, we've got a 1 positive charge. For chloride, we've got a 1 negative charge. Those go together 1 to 1. So we're going to have RbCl. You could also swap and drop if you want to do that every single time. That is an option. And then we also have the cobalt and the hydroxide, and we're also going to swap and drop these. So we're going to have CO. We put the OH in parentheses because it's a polyatomic group. We want to say that we've got 2 of this whole group. And we do that by writing the 2 outside of the parentheses. So this would be our other product. And then I'll give you like 30 seconds to balance this. All right, to balance this, we are looking for something that is not balanced on the left versus the right. One of those things is chlorine. So we're going to balance our chlorine first. So Cl, we've got 2 on the left, we've got 1 on the right. To get those balanced, we want a coefficient of 2 in front of our rubidium chloride that's on the right side. That gets us up to 2 for our chlorines. When we did that, we also messed up. We adjusted our rubidiums, and so we're going to balance rubidium next, Rb. So Rb, now we've got 2 on the right. We have only 1 on the left on the reactant side. 1 is not equal to 2, and so we need to put a coefficient of 2 in front. That will get our Rbs balanced out. And then we adjusted our OH when we did that, and so we're going to look at OH next. OH, we've got 2 on the left, and look at that, we've got 2 on the right. So we are balanced. And then to check, we'll look at our last thing, which is our cobalt. 1 cobalt on the left, 1 cobalt on the right. All squared up, all balanced. Ship it. Questions about balancing chemical equations, single replacement reactions, double replacement reactions, combination reactions / synthesis reactions, decomposition reactions, combustion. Those are some of the things we talked about today. All important ideas. I usually ask 2 questions about types of reactions. So combination, decomposition, single replacement, double replacement, or displacement. Those usually, 2 of them usually show up on the relevant exam, but that will be exam 3. So you don't have to know that for our exam on Tuesday.